All right. Welcome everybody to the Georgia Tech Graph Theory Seminar. Our speaker today is Zi-Xia Song from University of Central Florida, and she will tell us about breaking the degeneracy barrier for coloring graphs with no KT minor.
Thank you, Anton, for the invitation. I noticed that this week, Luke is giving 2 talks this week. This is a pure accident. We didn't mean to make this week about Hadwiger's conjecture only. So this is a joint work with Sergey, Norin, and Luke Postle. Last year, I was on sabbatical leave. Here, I would like to thank Sergey one more time for hosting me, for having me on this beautiful project. Without Sergey, I won't have this talk here today. And I would also like to thank Robin for teaching me graph minors. This was Robin who did me back in July 30, 2004 on the Phantom. He is was the best advisor anyone can ever ask for. So now let me get started on the topic here. So I think Luke makes my talk very easy now. He gives really detailed proofs for his during his talks. So I'm going to just give you more stories today, and tomorrow evening at 9 p.m. Eastern time, Luke will give another talk. So I highly recommend you to attend Luke's talk. So let me define what is a minor here. Given graphs G, H and G here, we say G has an H minor if a graph isomorphic to H can be obtained from a subgraph G prime of G by contracting edges. And in addition, if the set of contracted edges forms a cut in the subgraph G prime, we call such a minor an odd H minor, an odd minor here. So this definition might be really abstract to beginners. So in this definition, you need to know the empty set is a cut. So this tells you every graph is an odd minor of itself. Every graph, of course, is a minor of itself, right? So if G has an odd H minor, then G would have an H minor. However, the converse is not true. So to give you a better understanding of the concept, I'm going to define this one slightly differently, okay? So I have given you 2 graphs. So an H expansion, in our paper, we also call it a model of H in a graph G. So it's a function eta here with domain VH union EH here, such that if you take any vertex in VH, from H, eta V is a connected subgraph of G. From a connected subgraph, you can take a tree out, spanning tree out, right? So eta V for the H expansion is going to be a tree. And the trees here for different vertices, these trees must be vertex disjoint. So we need these trees here to be pairwise vertex disjoint. Now for edges, for every H UV in H, eta E is going to be an edge in G with one end in the tree corresponding to V and another end in the tree corresponding to U. So this definition is more easy to follow here. So for this one here, it's easy to see that G has an H minor if and only if G has an H expansion. And for the talk here, also in our papers, we say H is an L-bounded minor of G if and only if here G has an H expansion such that every tree you picked has at most L vertices. Every tree you contracted to a single vertex has at most L vertices. So this is called L-bounded minor here. Let me say a little bit more here. What do we mean by even order minors here? Now, the trees, if you put all the trees together here, the trees are called the nodes of the expansion. Now we use this big union eta here to denote the subgraph of G with this as its vertex set, all the vertices in the trees you picked. And the edge sets here includes all the edges in each tree you picked, plus the edges here for each E in H. We have eta E here in my original graph G. So this subgraph here, we use this one to denote this subgraph. Now we say an H expansion eta is even or bitype if this one is bitype. Or you say if H is an even minor of G if this one is bitype. And this expansion eta is odd if you can partition the vertices of this subgraph here into two parts, A and B, such that every edge of each subtree you picked has one end in A and the other in B, and every edge eta E here has both ends in A or both ends in B. So exactly you see how the edges inside each tree will be contracted to form a minor, right? So those edges are running between A and B. Or you can understand it differently by thinking of coloring the vertices of a big unit eta here with two colors, so that all the edges in each subtree you picked are bichromatic, but the edges running between the trees you picked, exactly one edge you picked, there is monochromatic, they receive the same color. So this is, I try to give you the detailed definition here for this late afternoon talk. So now let's see here. With this definition, you can see one example here. This would be an order K4 expansion or an order K4 minor here. This is order K4 expansion. By the way, please feel free to stop me if you have any questions. And let's see here. Oops. So for example, you can ask yourself, does the Petersen graph have an order K5 minor? So if you think a little bit, you will see the answer would be yes. Now this colored edges gives you 5 different trees, and the vertices are colored by color 1 and 2. And then you see order K5 minor. So just in case you plan to read our papers, I try to give you more examples to make it easier to read. Now, for example, does Kn have Kn plus 1 minor? Now, if you think a little bit, you would know the answer is yes. If you're contracting a matching of size n minus 1, you get 1. But you don't have a minor click minor on n plus 2 vertices. Okay, the same question now, I replace the regular minor by an even minor. Does Kn have an even Kn plus 1 minor? Now the answer would be yes. Why? Because every minor of a bitype graph is even, right? So this is tricky here. So this actually we use apply a lot for our paper for order Hadwiger's conjecture. The next one here is, does Kn have an order K3 minor? So this philosophy is due to Andrew Thomason. I really like his paper, his one paper he wrote on the extremal function for complete graphs. It's really beautifully done. And this is his philosophy. So if you think the answer is going to be no, so you can see why. So let me continue here. This is just the pop quiz I created. And okay. So now let's move on here. So we knew a lot of we can characterize graphs using forbidden minors. And one that everyone knows is about the planar graphs. And another one here, we know the famous graph minor theory due to Robertson and Seymour says that the finite graphs are well quasi-ordered by the minor relation. So we knew this one. So just a little motivation for the definition of minors here. Now let me say here, the notation I'm going to use during my talk. So the vertex coloring here is going to be a proper vertex coloring. So we use chromatic chi-g. Now Hadwiger number here is defined to be the largest integer t such that kt is a minor of g. So this means minor relation here. Kt is a minor of g. And this is the independence number. This is the clique number. So I will not say, everybody knows. And we use a d of g to denote the density of a non-null graph G here. It's the number of edges divided by number of vertices of a graph. It's half of the average degree you normally use. So we knew this, the chromatic number is always bounded below by the clique number, and we know the equality holds for many families of graphs. Now, however, so not however yet, sorry, as I said, I teach 2 classes today. Now, if a graph contains kt as a subgraph, we know chromatic number is at least t, right? Now, conversely, you can ask yourself, if chromatic number of G is t, now does G contains kt as a subgraph? We know this is far from being true, right? Because now Eldish back in 1959 proved that for every integer k, you can always find a graph G with chromatic number at least k and a growth at least k. So you were wondering what causes the chromatic number so high? Now, is it possible topological complete minor here is the troublemaker? Since Xinxin is here, you know, he would so disagree with you, right? And their recent result on Kelman's and the Simon's conjecture here says that every 5 connected non-planar graph contains a topological K5. So I wanted to say Hadwiger's conjecture is false for any t at least 7, but true for t at most 4. It remains open for 5 and 6. Xinxin and his students did a lot of work on the next open case t equals 5. And then, so we were wondering here if kt minor here was the troublemaker. If I need a t, exactly t colors to color, is it true that my graph must contain a kt minor? So now let's look at the small values of t. And it's trivial when t is 2, at most 2 here. Now when t is 3, you can see from this line here, no k3 minor means I think my graph simply doesn't have any cycles. So it would be 2 colorable. Now for t equals 4, I'm lazy here. I simply use series parallel graph. So no k4 minor means my graph is series parallel means it's 2 degenerate. 2 degenerate means every subgraph of this graph G has a vertex of degree at most 2. So this gives you the fact that my graph is 3 colorable. Now for t equals 5, you want to prove no k5 minor implies my graph G is 4 colorable. Now this follows from Wagner's theorem on graphs with no k5 minors and the 4-color theorem. Okay, now before the 4-color theorem, this pretty much the story on this question. And the Wagner's theorem actually inspired Hadwiger to make the following conjecture. You see, Wagner's theorem was from 1937, and Hadwiger made the conjecture in 1943 here. So it says for every graph G, the Hadwiger number should be at least the chromatic number of G. Now, equivalently, you can restate this conjecture as for every integer t, a positive integer t, every graph with no kt minor is t minus 1 colorable. So these 2 formulations are equivalent. It depends. I use both during my talks. Okay. Now from the previous slides you see here, this is easy when t is at most 3. I want to mention one thing here. Paul Seymour gives a beautiful survey back in 2016. In his survey, he commented that this conjecture perhaps is the most famous one in graph theory. Now for t equals 4, Hadwiger himself gave a proof, and Dirac later gave a proof. I don't think according to the survey given by Toft, Dirac did not know the proof of given by Hadwiger here. And Wagner later on also had a proof for t equals 4 case. All proofs are different. And for Wagner's proof, you can find it in Distel's book for age maximal K4 minor free graph. So he has the complete characterization there. Now, when t is at least 5, now Hadwiger's conjecture would imply the 4-color theorem. And to see why this is true, you can do the following. Given, if you give me a planar graph, I can form a new graph H with no kt plus 1 minor here. And you form your graph in this way. Now the new graph, by Hadwiger's conjecture, the new graph is t-colorable. So this gives you the fact that G is 4-colorable. So you can prove the 4-color theorem if Hadwiger's conjecture is true. Now when t is 5, now by Wagner's theorem, you see, I should add a Wagner and a 4CT here. The Wagner's theorem actually is equivalent to 4-color theorem. I don't need to add a 4CT here, it is here. For t equals 6, this was done by Robertson, Seymour, and Robin Thomas here back in 1993. Now this conjecture remains open for t at least 7. And I want to comment here, it is not known yet for the next open case. We should look for, if a graph has no K7 minor, then it's 6-colorable. So it is known that such a graph is 8-colorable, but we cannot prove it's 7-colorable yet. So this is the project actually I had in mind when I planned to visit Sergey. With my PhD, former PhD student, Martin Rolek, we made quite some progress towards this project, but we still haven't done with the project yet. We even got Robin involved back in like 3 years ago, but we didn't find a way to complete the remaining cases. So let me so tell you what is a strengthening of Hadwiger's conjecture. So Jarrett and Seymour in 1993 conjectured that every graph with no order kt minor is t-1 colorable. So you can see here from the definition of order minor, you can see this conjecture is substantially stronger than Hadwiger's conjecture. But still it's trivial when t is at most 3. You can see the proof here. No order K3 minor means my graph has no order cycle at all. So which means it's bipside. So it's 2-colorable. So for t equals 4, Catalin had a proof in 1979. The next case t equals 5 here, a proof was announced by Guénon back in 2005. When I prepared the talk, I still hasn't found his paper published yet, so I don't know the story here. And this one is open for t at least 6. So I want to show you what's new here. I did not collect all the results in this area, just the one here, a little bit here to give you some idea here. So it's true for C4 free graphs with sufficiently large chromatic number. Kuhn and authors proved in 2003. And later here, Reed and Seymour proved that this Hadwiger's conjecture is true for line graphs of multigraphs. And Chadanovsky and Fredkin here extended this result to quasi-line graphs. And you know quasi-line graphs contains line graphs. And the quasi-line graphs are color-free graphs. So the next one here, they give approximation of Hadwiger number and the chromatic number. It's 2/3 now. The conjecture is 2/3 should be 1. That's the conjecture. So with my undergraduate students, we add slightly more evidence to this conjecture by excluding induced cycles of length between here and here. And from this statement, you would see our proof actually relies on the strong perfect graph theorem. So we added a little bit more. next family here is the most interesting one for a reason. So graphs with independence number at most 2. So many researchers believe that if Hadwiger's conjecture fails, it would fail for the family, for such families. The counterexample would be here. And for this special family here, if you exclude a graph on 4 vertices with independence number at most 2, then Hadwiger's conjecture is true for such graphs. And later, Crisell extended it to graphs with 5 vertices, on 5 vertices, and the independence number 2. So you have this. To me, the most impressive result was this one by Maria and Postle here. For their paper title is called Packing Seagulls. They take as many copies of induced paths on 3 vertices. They have this proof here. So if you're so your click number here. So what remains hard here when the click number is less than a quarter of the vertices in your graph. And my former PhD student add a little bit to this family here by excluding a wheel on 5 vertices as an induced subgraph. Then this family also satisfies Hadwiger's conjecture. So these are the special families. Now, what about the asymptotic bonds or superlinear bonds for Hadwiger's conjecture and other Hadwiger's conjecture here? Now, Marder in 1968 considered the extremal function for click minus. So if every graph with average degree of this gives you a KT minor. So this means every graph with no KT minor is this number minus 1 degenerate. So that's why it's this colorable. So T is at least 4. And later, Kostochka and Thomason here proved that every graph with average degree of big OT square root T, this becomes square root log T now, has a KT minor. And we knew this bond is tight, and there is a construction here. So this implies every graph with no KT minor is big OT square root log T colorable. So this was the based upon on the chromatic number for such a graph. And Thomason later here completely determined the constant inside here. He proved that this alpha roughly is 0.638 for this one. So now what about other Hadwiger's conjecture? So Kostochka and Thomason's bond here was extended to order minus by Gillen, Jarrett, Reed, Seymour, and Veta in 2009 for order click minus. So that's pretty much the record before last year for this one, for Hadwiger's conjecture and other Hadwiger's conjecture. So in the literature here, as it was mentioned in Bruce Reed and Paul Simon's paper, so I have this paper listed in this way just in case you are interested to read their paper, so it's easy for you to find the paper. Mentioned in their paper says it is a commonly expressed counter-conjecture that for large P, Hadwiger's conjecture is false, and the best possible bond on chromatic number would be big OT square root log T. That's the one. In the same paper, they give the linear Hadwiger's conjecture. They believe there exists a constant C such that every graph with no KT minor is CT colorable. Now this conjecture later was also mentioned by Kobayashi and Moha and Kobayashi in different papers. So I just list all the reference here. And in the same paper here, Reed and Seymour proved that this is true if you consider fractional coloring. So this is true for in. So what we did last year, or before that, let me mention Hadwiger's conjecture, linear Hadwiger's conjecture, and the list coloring here. So we know Hadwiger's conjecture doesn't hold for list colorings, right? So Now, Kobayashi and Moha had the least linear Hadwiger's conjecture here. It says there exists a constant C such that every graph with no KT minor is CT choosable. And this, we knew they also mentioned that it may also be true that you can choose the constant C to be 1. Because as we know, this is true when T is at most 5. So later, David Wood, Barat, Joret, and Wood had this construction which disproves the above claim for C equals 1 for T at least 8. Now, if you plug in P equals 2 here, you would see no K6 minor is not 5 choosable, no K7 minor is not 6 choosable, but it is not known if no K6 minor is 6 choosable, no K7 minor is 7 choosable. This part, these two remains open here. Okay, that's all possible. I think I may have listed all possible conjectures related to Hadwiger's conjecture except Wood's one. Okay. Now, so last year when I visited the Sergey, when I walked into his office, he put on the blackboard, he said, let's prove every graph with no KT minor is little o t root log t true colorable. I was like, I don't know if I can solve this one. So as I said, without Sergey, we won't have this paper. Okay, his contribution was tremendous here. Now, we proved that for every beta at least 0.354, every graph with no KT minor is big OT log T beta colorable. Is exactly what Sergey wanted, and it's little O now. So this would disprove the counter-conjecture. So we put our paper on archive on October 21st, 2019. And 2 weeks later, Luke find a way to improve the second part of our proof and make beta to be a quarter. So for those who may not know, both Sergey and Luke are my academic younger brothers. I'm so proud of them. Okay, so so later we have these two papers combined, and now the final version is here. We posted on May 27th, 2020. Okay, so we have it here, and let's see. So later here with Sergey, we extended this one to all the Hadwiger's conjecture for beta at least a quarter. We also prove every graph with no order KT minor is big OT root log T beta colorable. And this year it was, I was very impressed. The Sergey and Luke had this one worked for list coloring. I was very impressed. And of course, this last June here, Luke made a further progress on the work we did here. He now make a beta here bigger than 0. So he gave an excellent talk yesterday, and once again he will talk about this one tomorrow at 9 p.m. So for this one, that's the current progress towards these 3 conjectures. Okay, towards these 3 conjectures. So let me say a little bit here. I would say a little bit. I mean, I deleted many more proofs because I noticed that Luke is giving too. I don't need to bore you with the details. So, but I still want to say a little bit about the proof sketch here, because Luke's proof now it would work slightly differently now for beta bigger than 0. So this is the one was mentioned in our paper. Now, how do you prove such a statement? So it suffices to show that for every delta positive, and you can find a large enough t here, such that for all positive integer t, every graph with no KT minor satisfies this condition. Is this colorable? So we are going to prove this statement here by considering the number of vertices in my graph. So So case one here, we would think when when I have small graphs here. So this means roughly the number of vertices in my graph is roughly t polylog t. So in this case, I would have chromatic number is big O t log t. So for Luke's current record here, his number, the beta there is going to be t times log t to the power 6, log t raised to the power 6 in his current proof. So how do we make this happen here? So we need to, for the graphs with independence number 2, I forgot to mention Duchet and Minius result because I'm going to mention it here. When alpha equals 2, this gives you, if my graph has n vertices, this gives you n over 3. So currently n over 3 is the best result. No one can improve this bond for alpha equals 2. So when Seymour wrote his survey back in 2016, he observed that the proof of Duchet minion actually gives you this property. If a graph has no KT minor, then you can find a vertex set with at least half of the vertices you have, such that the graph induced on X here is T minus 1 colorable. So the proof of Duchet minion would give you this. Later we find out Udo actually proved a stronger one. You can make the same thing, but chromatic number can be made to T minus 2. So with Kawarabayashi, we extended Duchet minions to order minus. So we have the same bond. So with this theorem here, you can quickly prove this. If G is a graph with no KT minor, then the chromatic number is bounded by this. So what you do is you just take a greedy algorithm, right? You take a X1 with at least half of the vertices that is T colorable, then you take a X2, and after these many steps, the remaining graph must be T colorable. So you just add up and you get this bond. So you get this bond. So when VG is small, roughly you are done. Okay, now what about the larger graphs? What do you do about the larger graphs? Okay, so when for larger graphs here, what do we do here? We choose a maximum collection of subgraphs, H1 through HR. They are all pairwise vertex disjoint and satisfies the density here of each HI is at least this, and the number of vertices is relatively small. Now in this case, we have two situations. One, I have enough number of pairwise disjoint subgraphs I can select, and one is I don't have this many. So the first case is, the second case is the most challenging one. So I'm going to show you in a little bit how does this one work. So if I have these many copies of, at least these many copies of vertex disjoint subgraphs, such subgraphs, so we can prove that my graph G here does have a HT minor, a KT minor here. So the proof of this one mainly follows the ideas of Thomason, this paper which determines the exact constant there. So for the when we prove this, the proof is technical, so I want to go over it. Just want to mention to you here, we do use a linkage. You should think. So I have a small click minor lives in each subgraph HI. How do I connect these small small minors into a big one? How do I connect? So this is a technical, so I want to go over it, but we will use linkage here. And we have a rooted minor and a linkage here. This one will be used. And this theorem will also be used in for order Hadwiger's conjecture. And I don't know if this is, I don't think this is used in the list for list coloring. Okay, for list coloring. Now for order Hadwiger's conjecture, here we are looking for an even KT minor. Okay, we are looking for even KT minor. So this is, as I said, this strategy here is applied to construct desired small click minor in each HI. And for our paper, this theorem was the only one which used the probabilistic method. So I give Sergey a big headache as I'm really not good at the probabilistic method. So you don't see much in our paper. This is the only place you see probabilistic method. So this is the case when you have enough number of this one. So I need to move quickly. So if I don't have this many copies of subgraphs, what do I do here? So you put all the vertices together, you look at the subgraph induced by this one, because the number of vertices is small. By the previous theorem, you knew this graph is colorable by this many colors. Now we try to convince you the remaining graph here is also colorable by these many colors. By the choice of the question is, how do you do that, right? So we prove in a way you can think of by contradiction. Suppose this graph is not colorable by these many colors. It must contain a critical subgraph with minimum degree at least this. So then this graph would have high enough density. And this is the place where we use the density increment argument here. So we are going to apply this theorem to the critical subgraph I find here. How do I do that? So this theorem tells you that if I have a graph G, so of course you have delta here, you have C, you have capital D here. If G is a graph with density at least C, and this S here is D over dG here, then G contains at least one of the following. Either a minor with density at least D, or a subgraph H satisfies these conditions, okay? So we're going to apply this theorem to the critical subgraph I found here, so that when I make a right choice of D, such a graph doesn't have a minor, a KT minor, does not have a KT minor. So which means it must give me a subgraph satisfies this condition. So this subgraph now, if you calculate, if you choose delta carefully, this would give you a subgraph. This H here would satisfy this density condition, this order condition here. So which means I can add this H to the sequence I selected. This would contradict to the maximum choice of R I picked. I choose R maximum here. So this is the very important theorem we call the density increment argument here. This was used through 3 papers, okay? And when you look at this theorem, one thing here you may want to know here, how do you make a choice for D? How to make a choice for D here? And Kostochka has a specific form for KT minus. If the density is at least this 3.2 T root log T, then you have a KT minor. And later here, Gillen, Jared, Reed, Simon, and Vita here proved that if you double, it's like a double, I put the 7 here, just make it look nice. I mean, you just 6.4. Double the constant here would give you an even KT minor. Because as Ruth mentioned during her talk last week, every graph contains a biptide subgraph whose density is at least half of the original graph, right? So you get a complete biptide subgraph here. That's why you just apply the previous theorem to the subgraph you find here. Biptide subgraph, you get an even KT minor. And for our order minor paper, we are actually looking for an even KT minor because of this theorem mentioned in there, because of this beautiful result proved in this paper. So let me not go there. I think I still have something left to say. I still have like 5 minutes.
10 minutes actually.
I have 10 minutes. Okay, I thought I have. My time is up. I made a mistake. I thought we started at the 3:30. Okay, let me not rush. I thought I ran out of time. So this one gives you a reason here, and you can see why we, for the order minor paper, we only consider even click minors when we in the proof. So this is how you make a choice for D. And you might be wondering here, when I do linkage, when I find try to find a larger click miner through these smaller ones, I never mention the connectivity of my graph, right? Why my graphs are highly connected? So you may want to see why my graph G and HIs are highly connected. So fortunately, we do have the theorem ready for us to use. So Marta proved back in 1972, every graph G contains a subgraph H with connectivity at least density divided by 2, right? We knew this one. Now for a contraction critical graph, to prove the Hadwiger bonds, so we can assume our graph is contraction critical. So what is contraction critical? Sometimes we say T contraction critical, means chromatic number of G is T, but any proper minor of G is T minus 1 colorable. So for this one, there is a question here in the literature. Is it true that someone may have conjectured it? I forgot to find out whose conjecture is this one. Is it true that every T contraction critical graph is T connected? So we knew it's true for T at most 5 by Dirac, and later Marta extended this one for T equals 6 and 7. So far, no one can prove it for T equals 8. But Kostochka proved the general bond here. All such graphs, T contraction critical graphs, are at least 2T over 27 connected. There is more development on this one. I didn't list it here since constant to us is not important. So we were using Kostochka's bond here, 2T over 27. Now another one here for all the Hadwiger's conjecture. For all the Hadwiger's conjecture, you don't have contraction critical subgraphs. You simply don't have this concept there. How do you guarantee the connectivity? In our paper, Sergey invented a weaker connectivity there. It works well for our proof. And Sergey also asked this as a question during this workshop in March. And asked here, is it true that every graph with chromatic number at least K contains a subgraph such that the chromatic number and connectivity and the chromatic number are still relatively high? So later on, quickly, Girard and Narayana here proved this beautiful theorem. And this theorem plays a very important role in Luke's new improvement on Hadwiger's conjecture. So this is the one. Now for this here, you might wondering here, what can be done next? As I said, I deleted many proofs. I don't want to bore you with the details because Luke is going to give you a better one. So here, to sum up here, this is what we had so far. And from Luke's talk yesterday, I knew are still open. Is it true here, every graph with no order KT minor is this colorable for every beta bigger than 0? And the same for this coloring. I haven't been able to do any research recently, so I won't be surprised if Sergey already have a solution to both of these questions. Okay, to both of these questions. And the next one I want to mention a little bit here. If you care about Hadwiger's conjecture for small values of T, one approach here is to consider the extremal function for KT minus. So for T at most 10 here, we know Marta proved it for P at most 7. Every graph with this many edges has a KP minor. And we refer this one as Marta's bond. Okay, so later Jorgensen extended the Marta's bond for P equals 8, and we have one abstraction here. This is cockade, so we will not define what is cockade here. So with Robin here, we extended this one to P equals 9. We have one additional graph found plus the cockade we obtained from Jorgensen's result. So in my dissertation, I do have a conjecture for KTM minor. All these graphs were found by hand. So don't be surprised, I missed the two graphs out. So now Denton did a computer search, they found that they added the two more to the conjecture. So I put a double plus here because Denton is still working on the paper. I still be able to say more about the progress on this paper. But in general here, Seymour and Thomas made the following conjecture. For every p at least one, there exists a constant n here, such that every p minus 2 connected graph on at least n vertices, and with at least this many edges has a kp minor. The connectivity here simply follows from the cocket. Now this cocket here is you can create such a cocket for any p. This cocket is, this 7 tells you this is a p minus 3 connected. So that's why they have p minus 2 here. If this is true, p minus 2 would be best possible. Now this conjecture is open for p at least 11. So for this one. Now with my former PhD student, Martin Rolik, we made this conjecture because for a reason, okay? We think maybe Marta's bound is true in the following sense. If you look at all the small counterexamples, they are all t minus 1 colorable. So every graph with this many, at least this many edges, either contains a kt minor or is p minus 1 colorable. So you can make this one 2t minus 6 if you like. If you are interested in working on linear Hadwiger's conjecture, you don't have to make this one t minus 1. You can make this one ct colorable for this one. So we proved that if this conjecture is true, then every graph with no kt minor is 2t minus 6 colorable. So since this conjecture is true for t at most 10, I put a 10 in the pink color because Denton's paper is not out yet. So so this is the one here. So otherwise it's open for t at least 11 for this one. Okay, I think I rushed. I think that's all I wanted to say. I think I rushed. I thought I stopped at 3:30.
Thank you very much, Zi-Xia. Let's all thank her. Are there any questions? Yeah, this is not a question, but maybe just a comment. You were pointing out how your paper appeared on the archive, and like a week later there was Luke uploaded
2
his
weeks
thing.
later, yeah.
2 weeks later, yeah. That's actually in the middle of those 2 weeks. He was visiting CMU to give a talk in the ACO seminar there, and he showed up and he was like, "So I said, have you seen this paper on the archive? let's get the constant to be, I want to get the constant to be just anything bigger than 1/4." I was like, "Yeah, okay, we'll see." And then like a few days later, he uploads his paper on the archive. So
Yeah, Ron was very impressed. Yeah, and I felt bad for Sergey because I didn't see any of this.
any more questions?
Can you hear me? Hello?
Yes, I didn't pause for any questions. I'm sorry.
So like, what are like the main obstacles when you in the odd minor proof? Like I understand you lose some
odd minor
density and stuff, but other than that,
I think Luca can tell you a better reason because you have to use Luke's new strategy now. So for the small graphs, not the small graphs, when you don't how do you do we have to be honest, I haven't read the paper, the new paper by Luke yet. I haven't read this one yet. So recently for some health reason, I haven't been able to do any research. The obstacles I can tell, I shouldn't say anything, as I said, I shouldn't say anything nonsense because Sergey may already have a solution here. I won't be surprised if Sergey already have a solution there.
Well, I guess I was asking more about your result with Norin for beta at least a quarter.
For beta at least a quarter there, the density increment theorem, that delta we choose is just happen to be, if when beta is a quarter here, that argument works. It comes from the proof. When later on you have to make sure I can add a H to my collection, right? So remember I said I'm going, this graph, if this graph is not colorable by this many colors, it would contain a critical subgraph H. It would contain a critical subgraph with minimum degree at least this many. And you are going to apply this one to the subgraph I had here. For this subgraph here, when you apply this theorem to this subgraph I found here, now for this subgraph, you are going to choose your delta carefully enough. Well, the density of H is going to be at least T log T a quarter, and number of vertices here is T log T 3/4. So delta equal, the beta is equal to 1/4. It just works beautifully for the argument. The 1/4 comes from here.
There's also a question from Rose in the chat about whether you can make use of signed graphs to attack the odd minors case.
I knew the odd minors is related to sign graphs. I haven't thought about it. I actually don't know. It's possible.
So do you think the current method could be improved to further improve this upper bound, like below log T, so log T or
getting
something?
rid of log T is really hard. We at least I had no clue. I mean, right now Luca has it to T times log T to the power 6. It's no longer log T. You can make it a log T, but getting rid of log T is really hard. This method won't work. At least you look at the small graphs, you see the log there, right?
Are there any more questions? If not, then let's thank the speaker again. And next week, our speaker will be our very own Young-Hoo Yo. So please tune in for that.